Today, we are going to see about ionic bonds. Having studied extensively about covalent bonds, now we will look at how ionic bonded materials behave and how they are different from covalent bonds. If you look at the periodic table, the leftmost elements are least electronegative and the rightmost elements are highly electronegative. That means the elements on the left side tend to give away electrons to become stable, and the elements on the right side tend to take electrons to become stable. So, when these two types of elements come together, the leftmost element transfers its electron completely to the rightmost element. The left element becomes positively charged, and the right element becomes negatively charged. Since positive and negative charges attract, they stick together. This kind of bonding is called an ionic bond. For example, group 1 elements can transfer one electron to become stable, group 2 elements can transfer two electrons, and so on. These variations in electron transfer decide the type of ionic bond that form. Let us take an example: sodium and chlorine. Sodium has 11 protons and 11 electrons. It becomes stable when it loses one electron. Chlorine has 17 protons and 17 electrons and becomes stable when it gains one electron. When they come closer, sodium gives away one electron to chlorine. After this transfer, sodium has 11 protons and only 10 electrons. So it becomes positively charged. Chlorine now has 17 protons and 18 electrons. So it becomes negatively charged. These two oppositely charged ions attract each other and forms sodium chloride. Now one interesting thing happened here. Sodium becomes smaller after losing an electron because its outer shell goes off. Chlorine remains almost the same size because it has gained one electron and completed its outermost shell. In the solid state, sodium is not bonded to just one chlorine. Each sodium ion is surrounded by six chlorine ions, one on top, one on the bottom, one in front and one behind, and one each on the left and right. Similarly, each chlorine is surrounded by six sodium ions. That means if you want to pull out one sodium ion, you have to break six bonds at once. So, even though a single ionic bond is weaker than a covalent bond, when arranged together, the entire structure becomes extremely strong. That is why melting an ionic compound like salt takes enormous heat because you need to break many bonds at the same time. Now let's look at few examples where different types of ionic bonds are made depending on the number of electrons it transfers. In the case of lithium, it has 3 protons and 3 electrons. To become stable, it must lose one electron. Fluorine has 9 protons and 9 electrons and needs one more to complete its outermost shell. When they come closer, lithium transfers its one outermost electron completely to fluorine. Now lithium has 3 protons and 2 electrons. It becomes positively charged lithium, and fluorine has 9 protons and 10 electrons. It becomes negatively charged fluorine. They attract each other strongly and form lithium fluoride, which is represented as LiF. Let's move on to the magnesium and oxygen. Magnesium has 12 protons and 12 electrons. It needs to lose 2 electrons to become stable. Oxygen has 8 protons and 8 electrons but needs 2 more electrons to fill its outermost shell. So, magnesium transfers 2 electrons completely to oxygen. After the transfer, magnesium has 12 protons and 10 electrons. It becomes magnesium 2 plus, and oxygen has 8 protons and 10 electrons. It becomes oxygen 2 minus. Both now have stable configurations and attract each other even more strongly because two electrons are involved in the transfer. This forms magnesium oxide called MgO. Now consider aluminium and nitrogen. Aluminium has 13 protons and 13 electrons. It has 3 electrons in its outermost shell, which it gives away to become stable. Nitrogen has 7 protons and 7 electrons. With 5 in its outermost shell, it needs 3 more. When both come together, aluminium donates its 3 electrons to nitrogen. Now aluminium becomes aluminium 3 plus because it has 13 protons and 10 electrons now, and nitrogen becomes nitrogen 3 minus because it has 7 protons but 10 electrons. They attract very strongly and form aluminum nitride, which is denoted as AlN. Now let's take another interesting example. Having studied about one full element and one more full element bonding ionically, now we are seeing an interesting case. Let's take magnesium. It needs to lose 2 electrons to become stable. When I bring a fluorine atom, the fluorine needs 1 electron to become stable. So, the magnesium transfers 1 electron completely to the fluorine and the fluorine becomes stable and negatively charged. The magnesium needs still 1 more electron to transfer. Let us bring another fluorine. This time, this second fluorine takes the remaining electron from the magnesium and it becomes stable. Now all three become stable. Magnesium loses one full outer ring and it becomes smaller, and magnesium becomes 2 plus because it has 2 protons extra than number of electrons it has. Now all these three elements get attracted to each other. Now this becomes magnesium fluoride, which is denoted as MgF2 because there are 2 fluorines in this bond. Now let's look at another one of the most important and interesting example. Let's take carbon. Carbon has 4 outermost electrons. When I bring 2 oxygens closer, these each oxygen require 2 more electrons to become stable. Carbon whereas require 4 more electrons to become stable. So what happens when these elements brought together? One oxygen and the carbon makes double bond. That means it shares 2 electrons each, and another oxygen shares 2 more electrons each with carbon. If you look at after the establishment of bonds, you see the carbon has 8 electrons in its vicinity and oxygen also has 8 electrons each. But unlike earlier bonds, this is not completely transferred. This is only shared. That means this is a covalent bond. This is called CO2, carbon dioxide, which is a covalent bond, where electron is not fully transferred. The electrons are just shared. Now let's take another case. Suppose I have one carbon and this time 3 oxygens. Carbon requires 4 more electrons. Each oxygen requires 2 electrons more. So what happens? One oxygen makes double covalent bond with carbon and oxygen becomes stable. Whereas this carbon gets now 6 electrons, it needs 2 more. But I have 2 oxygens, each requiring 2 electrons. Because there are only 2 electrons carbon can share, each oxygen shares 1 electron with carbon. So now there is a carbon and there are 3 oxygens, whereas one oxygen double bonded, another 2 oxygens bonded with single bond. Whereas these 2 oxygens require 1 more electron to become stable. If you consider entire combination as one single molecule, this is called CO3. Now, this CO3 molecules require 2 electrons to become stable. Let us consider I am bringing calcium closer to it. The calcium has 2 electrons at its outermost ring, which has to be sent out to become stable. Now, when I bring calcium closer to this CO3, calcium tend to give 2 electrons and CO3 tend to receive 2 electrons. So each of the oxygen in CO3, which made single bond, receives this extra electrons from calcium. Now calcium becomes positively charged with 2 protons, and this CO3 molecule is negatively charged with 2 additional electrons. Now what happens? This is a negatively charged molecule and this is positively charged atom. They both come closer because of the opposite electrostatic force. They get ionically bonded to each other. Now the question is this element a covalent bond or an ionic bond? Let us look closely. In the case of Ca, that is calcium bonding with CO3 as a single molecule is an ionic bond. So between Ca and CO3 together is an ionic bond, but between CO3, C and O is a covalent bond. That means this element is a mixture of ionic and covalent bond. If you look at the element structure, it will look like this, where these larger atoms are calcium and the smaller combinations of CO3. This is how the element is arranged. The marble is calcium carbonate. This is a combination of ionic and covalent bond. Most of the rock you see are combination of ionic and covalent bonds. This type of mixture of ionic and covalent bond is called as ceramic bonds. So anything you call as ceramic, that means this material is made of the combination of ionic and covalent bonded materials. One of the interesting properties of ionic materials, especially ceramic materials, is their exceptional bond strength. The ionic bonds between the atoms are so strong that when a small mechanical force is applied, the atoms cannot move at all. Because of this rigidity, when the applied force increases beyond a limit, these materials do not bend, they simply break. Bending requires atoms to shift slightly from their positions. But in the case of ionic or ceramic materials, such movement is impossible due to the very strong electrostatic attraction holding each atom firmly in place. So, if you continue applying more force instead of bending, the materials fractures suddenly. That's why ionic and ceramic materials can only be broken or crushed into powder but can never be bent or reshaped. Also, since every atom in this material is bonded with multiple surrounding atoms at the same time, melting them is extremely difficult. It requires very high temperature and enormous heat energy to break all these strong ionic bonds together. This is exactly why, in high temperature applications such as furnaces and industrial heating chambers, the inner surfaces are lined with ceramic tiles. These tiles do not melt or deform easily, even under intense heat, because of the strong bonding within the ceramic structure. Now, another interesting property of ionic compounds, that's called dissolving. When you put salt into water, water molecules being polar pulls the sodium and chlorine ions apart. Each water molecule has a positive side and a negative side. The negative side of water attracts the positive sodium ions, and the positive side of the water attracts the negative chlorine ions. The water molecules surround and pull the ions away from the crystal one by one. This process, where all the ionic bonds are broken and the ions are separated and surrounded by water, is called dissolving. That's why when you dissolve salt in water, the salt disappears. Sodium and chlorine ions are floating separately in water, invisible to the eye. However, not all ionic components dissolve easily. Compounds like calcium carbonate, where two or more electrons are exchanged, form much stronger bonds. These cannot be broken easily unless the solvent has very high capacity to separate ions. Now let's talk about electrical property of ionic bonds. Electrical property means the ability of a material to conduct electrons from one place to another place. In covalent bonded materials, the electrons are tightly shacked and locked, so they cannot move. That's why most covalent materials are non-conductors except for graphite. In ionic bonded materials, the electrons are already transferred and tightly held between positive and negative ions. So, in solid form, ionic compounds cannot conduct electricity because there are no free electrons. However, when ionic compounds dissolve in water or melt at high temperatures, their ions becomes free to move. These moving ions can carry current. So, in liquid or dissolved state, ionic compounds can conduct electricity. That's why solid salts cannot conduct, but salt water does. So, to summarize, ionic bonds form due to complete transfer of electrons between atoms with high and low electronegativity. Each atom in an ionic solid is bonded with several other atoms, making the structure very strong. Ionic solids are hard but brittle, and they cannot bend, they only break. They have high melting points because breaking all bonds together needs enormous heat. Weaker ionic compounds like sodium chloride dissolve easily in water, but stronger ones like calcium carbonate do not. Ionic solids are non conductors in solid form, but conduct electricity when dissolved or molten. Ceramic bonds are combination of ionic and covalent bonds, as seen in materials like calcium carbonate and ceramics, which are very strong and heat resistant. In nature, most of the materials you see, rocks, soil, stones, and ceramics, are made of such combination of ionic and covalent bonds. These materials are strong, rigid, and heat resistant, and they form the foundation of most structures around us.